Hello, everyone. Welcome back to this webinar series on machine intelligence on modern infrastructure. My name is Janakiram, and I'm going to be the presenter for today's session. So if you're attending this webinar series for the first time, let me set the context. So MI2 is a series focused on two aspects. One is machine intelligence that primarily covers IoT, artificial intelligence, deep learning, and the emerging technologies in the space of AI and ML. Modern infrastructure, which is primarily around Kubernetes, Istio, microservices, and of course, service mesh. This series attempts to bring the convergence of these two technologies, which is now delivering the next generation infrastructure and next generation of modern applications. Every session is accompanied by a demo, a live demo with code snippets, tutorials, and of course a recording of the entire session. So let's get started. Today's objectives for today's session, the objectives are the current state of the cloud. This is going to set us the stage for edge computing, and then we'll take a closer look at the evolution of edge, followed by the overview of Azure IoT Edge, some of the use cases and scenarios, and finally I have a detailed walkthrough and a demo that will help you understand how to configure edge devices and how to deploy applications. So before I go any further, I want to run a couple of polls just to make sure the audio and video quality is good. So if you're able to see the video and you're able to hear the audio clearly, please let me know. Excellent. Looks like the AV is good. All right. So one more poll just to make sure that I understand your background and the expectation. So how do you rate your IoT and edge computing skills? All right. So even if you are very familiar with IoT or just getting started with edge computing, you will find this session useful because I'm going to cover the big picture followed by a thorough walkthrough and understanding of Azure IoT Edge. So thanks for participating in the poll. It's time for me to get started. So what is the current state of cloud? Well, when cloud computing started, it was all about virtual machines that were running in a remote data center or storage that was offered in a remote data center. This highly centralized architecture closely resembles 90s client-server computing. For example, cloud, the remote data center or the remote infrastructure exposed by Amazon, Microsoft, Google, IBM, and others is the server, and the machine from which you are connecting to it and consuming the cloud resources is the client. So it closely resembles the 90s client-server computing. But at the same time, compute has gone beyond VMs. The first generation of cloud was all about VMs, virtual machines, where you could programmatically launch a VM and you could SSH into it and take control of the machine and install the software. But there is a dramatic shift in the compute where VMs are slowly getting replaced by containers. More and more workloads are moving towards containers, and that is another important trend. Almost all the public cloud storage offerings, and I'm talking about object storage, is complemented by a content delivery network. Today, whenever you put an object in a bucket or a container of the public cloud storage, you can click a checkbox to basically replicate and cache the data across multiple edge locations. But this edge is not the edge that we are talking about. This is the content delivery network, where it caches the frequently accessed content in a set of POP or edge locations. So that is another de facto trend. And finally, network has become extremely programmable. Today, if you look at the hybrid cloud, multi-cloud scenarios and how network traffic is getting routed and how load balancers, firewalls, and a variety of network components are configured, it is through APIs and programmability. So the same capability of SDN is enabling hybrid scenarios. Particularly when we look at the combination of software-defined network with some of the emerging networking technologies like service mesh, they are opening up additional avenues. Some of the very recent trends like Google's Anthos, IBM Cloud Private, and some of the other container-based hybrid cloud platforms are heavily relying on the programmable network stack, and also a combination of SDN with service mesh. So this is the current state of the cloud. These trends represent how the cloud is currently being consumed, or how it is delivered to customers. But as I mentioned, cloud is going through a huge transformation, and we have seen multiple waves of innovation. So initially, cloud was all about compute, storage, and network resources, globally available, highly centralized set of resources. Because cloud made compute and storage extremely cheap and affordable, a lot of industrial customers and enterprises started connecting devices to the cloud. The data that was not persisted or aggregated or acquired is now streamed to the cloud because it is extremely cheap to store data in the cloud. So a lot of companies and a lot of industrial environments started to take advantage of the cloud by streaming the data coming from a variety of sensors and devices, and also use the cheaper compute power to process those data streams and make sense out of the raw data generated by these sensors and devices. And that was the next big shift in the cloud, and this was IoT PaaS. So if you look at Azure IoT, Google Cloud IoT, AWS IoT Core, all of them essentially give you a mechanism, a platform to connect devices and store data and process it in the cloud. But IoT was not sufficient, or it was not enough to address a lot of scenarios. While cloud enabled capabilities like big data and IoT, a lot of customers were not ready to move the data to the cloud. That is one challenge. The second one is the round trip from the devices to the cloud and back to the devices was too long, and it was increasing the latency. In a lot of mission critical industrial IoT scenarios, sending the data to the cloud and waiting for the cloud to process it and send the results back was just not feasible. So there had to be a mechanism where data could be processed locally and compute comes much closer to the devices or the sources of data. So that's how IoT led to edge computing. And today, almost every mainstream enterprise IoT platform has a complementary edge offering, an associated edge offering. And more recently, there has been a lot of focus on artificial intelligence. Today, cloud has become the logical destination for training and running artificial intelligence and machine learning models. Thanks to accelerators like GPUs, TPUs, FPGAs, it has become extremely cheap and also powerful to train very complex, very sophisticated ML models and AI models. But in most of the scenarios, a model that is trained in the cloud is going to be run in an offline environment. For example, you might have trained an artificial intelligence model that can identify the make and model of a car and automatically charge the toll fee for that vehicle when it passes through the toll gate. Now, since the toll gates are on highways and freeways with very little connectivity and almost with no network access, you need to run this model in offline scenario. So edge computing became the boundary for running these cloud trained AI models, but running in an offline mode within the edge. So that is how we are basically looking at the evolution of cloud and the waves of innovation. So cloud, the distributed or rather the centralized platform for aggregating, storing, and processing data with high performance computing. IoT brought in all the devices to the cloud with a lot of data. Edge made cloud decentralized by bringing compute closer to the data source. And now it is AI that is actually driving the next wave, where cloud is becoming the de facto platform for training the models, and Edge is becoming the de facto platform for running the models. So one is called the training, the other one is called inferencing. So what exactly is edge computing? Well, edge computing makes the cloud truly distributed. As I mentioned earlier, the current cloud, or rather the previous generation of cloud, was almost like a mainframe or almost like a client server architecture where very little processing was done on the client side, but all the heavy lifting was done by the cloud. But with all the innovations in the hardware chips and with the affordable electronics and silicon, it makes more sense to bring compute down to the last mile and actually keep the compute closer to the devices. So that's when edge computing becomes more and more viable, where you don't need to rely on the cloud for all the processing and data aggregation, collection, processing, and querying. Instead, you could actually run a computing layer that is very close to the devices. So the edge computing mimics the public cloud platform capabilities. For example, when you dissect an edge computing platform, you would notice that it almost has all the capabilities of a typical public cloud IoT PaaS. It has device management, it has data ingestion, it has stream analytics, and it can run machine learning models, and it can run serverless functions. So all of those are capabilities that are predominantly available on the public cloud, but with edge computing, they all come to the last mile delivery point and run very close to the source of the data, which is sensors, actuators, and devices. The biggest advantage of deploying an edge computing layer is that it reduces the latency by avoiding the round trip. And it also brings in the data sovereignty by keeping data where it actually belongs to. For example, in a healthcare scenario, it may not be viable or it may not be compliant to actually stream sensitive patient data to the cloud where it is getting stored and processed. Instead, the patient data should remain on-prem within the hospital premises, but it still needs to go through a lot of processing and find out very useful insights. So in that case, the edge computing layer is going to stay close to the healthcare equipment with connectivity back to the cloud. And the architects and the customer engineers will decide what data will stay within the edge boundary and what will actually cross that and move to the cloud. Maybe anonymized data that doesn't have personally identifiable information and it doesn't have any non-compliant data will automatically move to the cloud, but the rest of the data is going to be ingested and processed right at the edge that stays within the premises of the hospital. So edge computing is the layer that sits in between the devices and the public cloud, delivers low latency processing, and keeps the data local so that you're compliant and you maintain the privacy, confidentiality, and security of data. So this is the big picture of IoT, because to really appreciate edge computing, you need to understand how IoT platforms are designed and how IoT solutions look like. So one end of the spectrum, you have devices, and these devices are either sensors or actuators. So sensors generate data, for example, a temperature sensor, a humidity sensor, pressure sensor, and so on. They generate data that is going to be acquired and ingested into the cloud. Then there are actuators, and these actuators are like switches and bulbs and things that you could switch on and switch off that have electromechanical interface. So those are called the actuators. Both sensors and actuators are commonly known as the devices. So when I say a device, it could be either a sensor or an actuator. So the devices connect to the edge, and the edge acts as a gateway, abstracting the devices that are at the lowest level of the spectrum, and that actually connects to the public cloud. Now, on the cloud side, we have two touch points for the edge or the devices. One is called the device registry, that is primarily used for onboarding the devices, and it is a repository of devices. Every device that is connected to the IoT platform has an identity within the device registry, the authentication, authorization, and the metadata of the devices is stored in the device registry. If you're familiar with an enterprise corporate directory scenario, think of the device registry like an LDAP of devices. So you can query that to get a lot of metadata and useful information about every device connected to the platform. The public cloud PaaS also, IoT PaaS also exposes a data ingestion endpoint. And this is the high velocity, high throughput endpoint where the sensor data gets streamed. Typically, this could be Kafka if you are doing it yourself, or it could be Azure Event Hubs or Amazon Kinesis or Google Cloud PubSub. So it is the pipe that basically acquires the data and passes on to the data processing pipeline. Now, both the device registry and data ingestion endpoints are connected to a message routing policy. So this is where you actually create a rules engine, or you basically create some kind of a policy that is going to define how the data flows. For example, some data needs to be batch processed, where you collect first and then process. In some cases, you need to perform real-time stream analytics. So if you are actually performing queries on data as it comes, that is called the hot path analytics. And if you are storing and processing the data over a period of time, it is called the batch processing. Now, both the raw data, which is about to go through either batch processing or stream analytics, is first persisted in a time series database or an unstructured database. And even the output from the batch processing and stream analytics gets persisted in the same database. So this is going to be the single source of truth for the entire platform. Now, from the same data store, we apply machine learning algorithms to basically find out anomaly detections and predictive analytics from the data that is coming in. And all of that is fed into an enterprise business intelligence platform, where you can actually run dashboards and alerts, and the entire visualization happens on the data warehousing or the business intelligence layer. So this is the big picture of IoT platform. You could actually map this to Azure or AWS or Google or GE Predix, Bosch IoT Suite, you name it. Every platform has a very similar architecture. It's almost like a blueprint for any public cloud-based IoT platform. Now let's zoom into Edge and understand what actually happens there. So coming back to why edge computing. So customers are implementing IoT in the cloud because they can do remote monitoring, they can do remote control of devices. For example, when a field supervisor is away from the manufacturing unit and he wants to control an equipment, he can actually pull out his mobile and tap a button that is going to control a pretty massive machinery inside the factory or inside the shop floor. So that is the remote control. Remote monitoring is basically monitoring the health of the equipment in real time. There could be NOC-like environments where engineers are constantly monitoring mission critical equipment. Customers are also implementing IoT because they want to merge the remote data from multiple IoT devices across multiple warehouses, multiple manufacturing plants into a central location and start processing it. So once you have these massive data sets stored in the cloud, you can of course apply very sophisticated algorithms in the form of machine learning and AI and make a lot of sense out of the data that is coming in. You could also take it back and apply some actions on the devices, and then it actually becomes predictive maintenance. But that is the use case for IoT in the cloud. When it comes to IoT on the edge, customers are preferring edge because they actually get low latency, tight control loop between the devices and the actual business logic that is controlling these devices. So the business logic, the analytics, the machine learning models that would typically run on the public cloud are now getting moved onto the edge because they provide a very low latency, closed loop, tight control mechanism for implementing that logic. The other challenge is public internet is inherently unpredictable, and particularly if you are in geographies like India, you know this really well. So you cannot rely on a 4G or an LTE or a 3G connection all the time to stream the data or talk to the public cloud. Instead, we need to have some kind of local endpoint, local touch point that can operate even when there is no connectivity or there is unreliable connectivity. And of course, privacy of data and protection of IP. For example, the healthcare use case that I mentioned is an example of why you need to have an edge layer right next to the healthcare equipment. It's all about privacy, confidentiality of data, and also protecting your IP. For example, you could have written a very specialized vertical specific AI model, and you don't want to run it elsewhere other than your own environment. So you could actually run that model on the edge computing layer, so your IP stays within your premises. So what is coming to edge? So if you dissect an edge computing platform, there are a variety of building blocks. Of course, there is data ingestion. This data ingestion is the high velocity, high throughput data endpoint, the Kafka-like endpoint that is going to ingest the data. Edge will also run message brokers that will orchestrate machine-to-machine communication. For example, device 1 talks to device 2 via the M2M broker. There may be unstructured storage, particularly to store the feed from video cameras and mics, and anything that is unstructured will go into object storage. And more structured data goes into time series database and NoSQL database. There is, of course, stream processing, which is a complex event processing engine that is enabling you to perform real-time queries and process the data as it comes. And to add additional business logic, there is a functions as a service, which is actually responsible for running lightweight compute. For example, for every data point, you want to convert Fahrenheit to Celsius, or you want to convert the timestamp from one format to another. You could do it either in stream processing, or if you need to do more sophisticated code, you could actually move that to functions as service. And of course, there is an ML runtime. For example, most of the edge computing platforms are capable of running TensorFlow Lite or Caffe models and even PyTorch models. So you can actually process the data that comes in more intelligently and take preventive measures and perform predictive analytics. So these are some of the core building blocks of edge computing layer. So connecting the dots, how exactly edge is adding value to IoT and industrial IoT. So 6 to 8 months from now, we'll actually see a very closed loop integration between the cloud and edge. And this is a reality today, but this is going to be more prominent in the coming months. So public cloud will be invariably used for implementing the learn function or the learn stage of your closed loop interaction. So you take massive amount of data set, store it in the public cloud, and use GPUs, TPUs, FPGAs, or ASICs to basically create a model that can identify either anomalies or outliers, or can basically figure out when a machine is going to die or it's going to face an issue. So all of that will happen in the public cloud. That is where the learning takes place. Then the model, which is trained in the public cloud, is deployed on the edge. And this is where the decisions will happen. For example, all the devices will stream their data, and this data goes through the ML model that is trained in the public cloud, and that is the decide phase. So the edge layer is responsible for making the decision or performing the decision management right at the edge device, right within the data center, very close to the devices. If there is an anomaly and if there is a problem that needs to be addressed, the edge layer can talk to an actuator and an action can take place. For example, in a industrial environment, a furnace could become extremely hot to an extent that it could be risky to run it further. So because of the machine learning algorithm, there is an anomaly that is found in the turbine or in the furnace, and immediately the subsequent action is to shut down the furnace. So the edge layer will now send a command to one of the furnaces, and automatically it gets shut down. And this doesn't need the intervention of cloud. Only when the data changes significantly and when there is a drift between the actual data and the predicted data, then you take the data again back to the public cloud, perform the training, which is the learning phase, and bring it down to the edge for the decision making. And when the decision happens, the action takes place within the devices. So this is the continuum where you have devices taking action, edge making the decisions, and public cloud implementing the learning process. So that is how edge brings tremendous intelligence to devices, whether it is Azure IoT, AWS IoT, Google Cloud IoT Edge, or some of the independent vendors like Foghorn, Swim.ai. Some of these vendors are actually implementing the exact same workflow to empower customers to exploit the cloud for performing the training, deploy the model for inference, and let the edge take control and perform the decisions while the devices are going to take the action. So this is the tight loop interaction between all the three players. So to take a different perspective, let's look at this from a different dimension. So there are data sources, and by the way, edge computing is not confined just to IoT. It could be even for non-IoT use cases. So anything that generates data can be fed into an IoT. Even cameras, even clickstream analysis, gaming, a lot of use cases are relevant for the edge deployments. So there are, it's basically like a three-tier architecture, but this three-tier architecture is not the traditional three-tier that we are familiar with. There is no app server, there is no database, there is no middleware, there is no front end. So this is not a traditional three-tier architecture, but in this three-tier architecture, the first tier is the data source. And in an industrial IoT environment, this could be a set of devices that are generating the data. Then there is an intelligence tier, and this intelligence tier is running the machine learning models, and this intelligence tier cuts across the cloud and the edge. So there is a very well-defined boundary between edge and cloud, where the training takes place on the cloud and the inferencing is run on the edge. But collectively, this overlap between the cloud and edge is the intelligence layer. And then there is an actionable insight. So the actionable insight is sending an alert to the relevant stakeholders, or populating the dashboards and showing some visualizations, or even the edge taking an action to immediately shut down a faulty machine, or controlling an actuator. All of them are actionable insights. And again, the actionable insight takes place on the edge. So this is not the physical boundary, but if you logically look at the whole architecture, so there is a data source, which is the original endpoint from where the data is acquired, or the origin of the data. Then there is an intelligence layer where the training, constant training and inferencing takes place. And then there is an insight layer where you actually visualize the outcome from the intelligence and also perform actions based on those insights. So that is one way of visualizing edge computing. So coming to Azure IoT. So Azure IoT is not very different from the architectural design aspects that we have been discussing so far. So you have Azure IoT Hub, which is the device registry in the public cloud, and that is interfaced with a variety of components. IoT devices can directly talk to IoT Hub as long as the device is capable of talking to the public cloud. For example, it has an Ethernet or a Wi-Fi interface and can make outbound connections. It can directly talk to Azure IoT Hub, and it can perform a handshake. But there could be some devices that may not directly talk to the public cloud. For example, very low footprint, highly resource constrained microcontrollers that cannot really run a TCP stack and make an outbound Wi-Fi call, outbound internet call, can actually talk to the edge using very lightweight protocol or a lightweight communication mechanism. And then the edge will act as a proxy, forwarding the data coming from these devices to the public cloud IoT Hub. That is one of the biggest use cases of edge computing, translating the protocols, the transport protocols, as well as wire format protocols. For example, your devices might generate very legacy proprietary formats based on things like OPC UA, or they could be very modern and they are capable of generating JSON payload. But ultimately, your business logic expects the data in a specific format, so you could actually stream that to IoT Edge, and IoT Edge can standardize or normalize the data irrespective of the origin, and then sends it the way the IoT Hub and the business logic expects it to be. As you can actually see, the IoT Edge is the layer between the devices, let's call them the child devices, and the parent device is going to be the Azure IoT Edge, and that talks to IoT Hub, which is the device registry. And remember, device registry is the repository and the metadata that basically consists of the entire collection of the digital identities of the devices that are connected. So coming to Azure IoT Edge architecture, so you have devices that are flagged off as edge devices. So for example, when it comes to Azure IoT Edge, you don't onboard devices that are technically very different from other devices. If your device is capable of running Azure IoT Edge runtime, you could flag it off as an edge device, which means it is capable of talking to other devices. So that is the first thing. So you will onboard devices, and some devices will be flagged off and will be basically earmarked as edge devices because they are capable of running the Azure IoT Edge runtime. So every IoT Edge device basically has a layer called the Azure IoT Edge runtime. And this is responsible for securing and maintaining the runtime of the edge computing environment. And then on top of that, we have an IoT Edge agent. And the responsibility of this is to basically maintain a connection to the cloud and to make sure that the edge computing is maintaining the desired state of configuration. For example, when you change the configuration of a device connected to the edge and the edge happens to be offline, it is the responsibility of the edge agent to basically synchronize the state of the device when it comes online. So that is going to maintain the connectivity and the synchronization with the public cloud so that even during offline, when you change the state, it gets synchronized when the device comes back online. So that is the job and the responsibility of IoT Edge agent. Then we have IoT Edge Hub, and this is basically the replica of Azure IoT Hub. They expose exactly the same API, same interfaces, and it is compatible with the public cloud-based Azure IoT Hub. Devices talk to each other via the IoT Edge Hub, and this is responsible for the communication and M2M mechanism between the connected devices. And then there are multiple modules, and these modules are essentially Docker containers that are running the business logic. For example, you want to acquire data from a sensor. How do you implement that logic? Well, you write a Docker container, you create a Docker container, and you push that image into the Edge runtime, and the instantiation of that container image will result in a module. And this module knows how to acquire the data from a set of sensors connected to one of the devices. Similarly, you want to operate an actuator, and the way to deploy your code is to turn your code into a Docker image, push that into the Docker Hub or the private registry, and then let the Edge agent pull the module as the container image and run it on top of the Edge runtime. So you can actually stack multiple modules on top of each other, and just like Linux pipes, the output of one module is fed as input to the other module, which means there could be a module responsible for acquiring raw data, and the output of that module is fed to a stream analytics module where you are aggregating based on a time window. And then the stream analytics output is sent to a machine learning model where you're performing anomaly detection. And then the action is actually taken in a serverless function that is again deployed as a container. So you can daisy chain multiple modules, and each module is basically responsible for one task at a time. And the best practice is to map one module to one sensor or one actuator so that you can basically map the device characteristics and the business logic. And you can also control these modules from the public cloud even when the edge device is offline or there is no connectivity. And when you modify a module during the offline mechanism, the job of edge agent is to synchronize it back when it gains connectivity. So that is going to ensure that your modules are always up to date. And this is done through a concept called module twin. So if you're familiar with IoT, there is a concept called device twin, which is a digital replica of your physical device, and it contains the metadata, state, and the variety of state representation of your physical device, and that is called the digital twin. And in the programmable aspect, you never directly touch the device. You basically modify the digital twin, and it is the job of IoT platform to synchronize the changes made to the digital twin to the physical device. And when physical device gets changed, again, the platform will synchronize the state with the digital twin so that you can always query the most recent state and the metadata. So that is digital twin. Just like the device's digital twin, module also has a device twin, because technically a module is an interface between the physical device that is connected to the edge and the cloud. So we are going to build an end-to-end demo, and this is going to clarify a lot of concepts. Basically, everything that we discussed so far will be covered in this demo. So what are we going to build, and what are the steps involved? Well, I'm going to show you a live device. So if you can actually see my screen, this is a Raspberry Pi, and this Raspberry Pi is connected to what is called as Sense Hat. The Sense Hat has an 8x8 LED matrix, and it comes with a bunch of sensors like temperature, humidity, pressure, and so on. The module that I'm going to build is to basically control the color of the LED matrix. So we are going to okay, I see there's a problem with the frame rate. So let me, okay, this is going to be slow, but I guess you can actually understand the scenario here. So we're going to build a module that will control the LED matrix on this device. But at the same time, we're also going to configure this Raspberry Pi as one of the edge devices so that it represents the LED matrix, the actuator, as a module. So I want to make sure I get the frame rate right. So I'm going to close this and launch the video again. Just give me a second. Sorry about this. I just need to make sure I'm able to stream the video. It's going to take one more step. I need to make sure that I'm using Wi-Fi and not any other. Right, never mind. I'm actually going to use the webcam and show you the demo. So don't bother about it. I'm going to show you this in a different form. All right. So the Raspberry Pi is going to be configured as an Edge device, and we're going to install the Edge runtime followed by the Edge Hub on that, and then we'll go ahead and register that as an Edge device with the IoT Hub, and then we'll actually build a Docker container that acts as the module to control the LED matrix. And finally, we'll deploy the module, and I'll also show you how to update the module. For example, every time you want to do a firmware upgrade or every time you want to push a new module, you can actually push that from the command line or from the portal. You can also implement a continuous integration and a delivery pipeline to automatically push the most recent code, business logic as the module right into the Edge device. So let's get started. Now, the first thing is to basically create a resource group. So if you're familiar with Azure, you will actually notice that I created a resource group called MI2. And within that resource group, I actually created an Azure IoT Hub. So the Azure IoT Hub acts as the device registry. It is also responsible for M2M, but predominantly it is a device registry where we are going to register all the devices. Now, once the IoT Hub is in place, we actually go ahead and register a device. For example, here you notice that there is something called add an IoT Edge device. So you click on that and then give a name, for example, Pi2, and then click on save button. This is going to generate a set of credentials, and these credentials are required for us to connect the device. Now, once we have this generated, we are going to configure the actual device. So let's say I generated the credentials for this device. I can also use the command line for that. So this is the first command that I'm actually running to create, to add the extension. This is completely optional in case you're running the most recent Azure CLI. You don't need anything else. But to make sure you're able to talk to IoT from the CLI, you need to install this extension. Then I'm creating a resource group. In Azure, a resource group is a logical boundary of all the resources that belong to a deployment. So we go ahead and create a new resource group called MI2 in US West. And within that resource group, I create an IoT hub called MI2 Hub. And SKU will define how many data points can be streamed at a given point and how scalable is the IoT hub. So in our case, just the S1, the standard tier, is good enough. So I have gone ahead and created the IoT hub called MI2 Hub. And once the device registry is in place, we need to create a device identity. So here you notice that I'm creating a device identity called Pi1. And this Pi1 is a logical representation of the Raspberry Pi that we have here. I'm giving a flag that says Edge enabled, which means this is not only a device, but it is also capable of running the Edge. And this is what is going to differentiate between a normal device with an Edge device. And this is absolutely important if you want to turn your device into an Edge device. So we created the digital identity, and then we need to retrieve the credentials of this device. So let me switch to command line. And when we actually run this, I have gone ahead and created some of them because it's going to take 7 to 8 minutes. I didn't want you to stare at the screen. So I've already created the resources. So now I'm retrieving the connection string that is responsible for authenticating our device with IoT Hub. Now, let's leave this as is. And I'm going to move into my Pi. So I have the Raspberry Pi here. So I'm going to first SSH into it. And once I have this running, I need to install the Edge specific packages. So first, I'm going to install Docker. This is actually the Moby runtime. Moby is the open source implementation of Runc, which is based on, which Docker is actually based on. So we implement, we deploy Moby runtime, which is nothing but a Docker compatible runtime. And then to manage the containers, we install the CLI. And once we have this in place, we are ready to install the Edge runtime. So after installing Docker or Moby, we actually go ahead and install the Edge runtime. And Edge runtime can be pulled from this URI, and then we'll use dpackage to basically install the Edge runtime. Again, I have already gone ahead and installed this. And once we have the Edge runtime in place, we need to make sure that we are connecting this Edge device to the cloud, to Azure IoT Hub. So how do we do that? Well, you can open this config file, and this config file is responsible for connecting your device, or it has the configuration that's responsible for connecting your device to the cloud. So here I'm going to populate the device connection string with the string that we grabbed from the CLI. So this is basically the credentials that we need to connect the Edge runtime with IoT Hub. So I populate the device connection string with the one that we just retrieved, and then all I need to do is to restart my IoT Edge runtime. So once we restart, it basically picks up the most recent configuration from the YAML file, and then the Edge device will start a handshake process with the IoT Hub. So once this is restarted, we can basically check the status. Okay, so this is going to show us the entire information. So now it is actually picking up the configuration from config.yaml, manually provisioning device, finished provisioning device. So this is done. So now it's in place. We can also look at more detailed logs by running the journal.ctl command. So this is going to show us a lot of information, and everything is green. That means there is no problem. Looks like the Edge device is now properly configured, and we are all set to deploy modules which will control the sensors and actuators. So when you actually run this command called sudo IoT Edge list, let me actually use another window to SSH and run this watch window. All right, so when we actually run this, you will notice there is Edge agent, and this has been running for about a minute, and then there is Edge Hub. Now these two are also containers, and if you look at the container URI, it is coming from Microsoft's container registry, and both these images are responsible for managing the synchronization and managing the connectivity with the cloud. And powering these two containers at the bottom is the actual Edge runtime. So now the runtime is ready, but it doesn't run any custom modules yet because we haven't deployed it. So now the goal is to basically deploy a module that can control the actuator. And by actuator, I mean the LED matrix. So how do we go about that? Well, I'm not going to build the actual container, but I will show you what goes behind this. So I have a directory called module, and here I have a set of Python files. For example, there is main.py, and this is calling hub manager, and this is what is expected in your module because this is establishing the connectivity and talking to the internal IoT hub running on the Azure IoT Edge, and then it actually calls hat.setColor. So that means we are actually importing this from hat, import hat color. So now there is another file called hat. This is where I implement the custom logic to set the color of the LED matrix. So main.py calls one of this, and then it automatically sets the color. And I have hardwired the color to be blue. Now, once I have all these things in place, what I actually do is I'll go ahead and build my Docker file. So here is the Docker file. There is a base Docker image, which has all the dependencies. So this is the actual Docker file, where I'm using the Raspberry Pi Debian stretch from Resin as the base image, and then installing all the packages that are required. And then I'm also running the pip install to make sure that I have the Python specific Azure client libraries. And it is also running other dependencies that are required. So once I build this base image, I use that to build my matrix image. So I copy all the Python files, and then this actually starts the hub manager, and subsequently it is going to control the LED. So assuming I have gone ahead and built this entire Docker image, and I have already pushed it to the Docker Hub, I can now go ahead and deploy this into the Edge device. So let's actually do that. Now I can click on Pi1. This is the device that we have registered. And in the portal, you will be able to see that it is running these two modules, Edge Agent and Edge Hub. And if you look at our window that we put in the watch mode, it's exactly showing the same. There is an Edge agent module and a Hub module, and both of them are also visible in the portal. So now let's actually deploy our matrix Docker module by clicking on set module. So this is how I'm going to deploy a custom module. So I click on add and choose IoT Edge module. If I want, I can also deploy Microsoft's own Stream Analytics module or an Azure Machine Learning module. Expect this list to become more comprehensive, because Microsoft is adding more and more modules that can run at the edge. But for now, we're going to choose IoT Edge module and push our custom module that can control the LEDs. So we will now use the same image that I have built. So Janakiram M / matrix V1. So that is the image tag. And I can also give the container create options, because I'm going to talk to the low-level GPIO. I need to run this in privileged mode. I also need to run this in the host network mode, because I'm actually making some outbound calls. So I want to make sure that I have access to the host network. So these are exactly the same settings that you would use with a Docker run command. So instead of those command line parameters, we are using a JSON file here that will contain the configuration settings. So this is how we basically define environment variables. This is how we define a lot of configuration that is used during the instantiation of the container. So that's it. Now we are all set. I'm going to click on save, and this gets added. The desired state is always running. Then click on next. This is how you feed the output of one container to the other, or one module to the other. In this case, we are not acquiring any data, but let's say I'm acquiring data from the sensor and I want to feed it to Stream Analytics. This is how I feed to the next container. So $upstream represents the upstream channel, where anything that I route to this channel will automatically become available to the downstream container. So it depends on how you actually chain, either upstream or downstream. But the idea is, this is how you feed the output of one container to the as an input of the other container. So this is the entire JSON file that is generated from the new module setting. Then we are going to hit on submit. Now, once we hit on submit, we are going to see some interesting things. So now it shows up in the portal. So matrix specified in the deployment, but not reported by the device. Now, when we actually come back and start monitoring this, very soon, you will notice that it is now deploying a new module called matrix. And now let me actually show you how this looks like. So I'm going to open the webcam. All right. So not sure of the lighting. I'm not really prepared for this, but I want to make sure you get to see this. All right. So here is the LED matrix, and it is glowing in blue, right? That's because the module is currently running. So let's keep this as is. And what I'm going to do now is to update the module and push the module again via the IoT Hub all the way to the edge device. And in this case, I'm going to turn the LED matrix into green. So we'll effectively update the module file to change the image from V1 to V2 and automatically push that to the edge device. So let me stop the webcam and take you back to the command line. So the previous version of the module, I actually deployed it from the portal. Now I can deploy it from the command line by modifying this file called module.json. And this is exactly the same file that the portal also generated at some point. And currently, we see that the image that is running is V1. So what I'm going to do now is to update the image to V2, leave everything else as it is, and push the module back to the edge via the IoT Hub. So now I come back to the command prompt and run this command where we are pushing a new version of the image via module.json. And now when we actually keep an eye on this, and I'll also open the webcam again. So now if you actually look at the terminal here, you will notice that V1 will be shut down, and in just a few seconds, we'll notice that the Raspberry Pi's LED matrix turns green, right? So there we go. Now the matrix container has been stopped. It shows failed. And in just a few seconds, it should get upgraded to V2. And okay, looks like there is. All right. Yeah, there we go. There we go. Okay, so now matrix is back, and this time as V2, and it immediately turns my LED matrix into green. So this is how you basically manage the entire workflow from the command line all the way to the cloud and back to the edge. This is the complete round trip. And because it is making use of containers, you could also implement a CI/CD pipeline where you are constantly updating, and it automatically gets pushed to the container registry, and from there to module.json, and from module.json to the IoT Hub, and all the way to the last mile, which is the Azure IoT Edge device. So this is how you basically deploy modules that represent business logic. Now, this is a pretty trivial, pretty straightforward example, but as you can see, I can easily augment this scenario with stream analytics. For example, if I'm acquiring the temperature and humidity data and I'm ingesting it every 10 seconds, I can now create a stream analytics query and basically use that to aggregate the data, and then run an ML inferencing module where I'm able to find some anomaly detection or perform anomaly detection, and write another module that controls the speed of the fan or controls an actuator responsible for visually showing the state. So I can do all of that just by daisy chaining and piping the output of one module with the other. And you can deploy multiple modules that are stacked on top of each other as your edge deployment. So that was the walkthrough about all the way from creating the edge device to writing your module and pushing it to the final device. So this entire script, along with the tutorial and step-by-step guide, is actually available. I'm going to share the link in an email to all of you after the webinar. And if you're watching this on YouTube, just click on more below the video, and you will find a link to an article on the news stack where I show you everything that I have done in the form of an article. So that actually brings us almost to the end of this session. So that was the demo of configuring and managing an edge device. So to summarize why we need edge computing, edge ultimately delivers low latency access. It exposes compute, storage, and networking close to the devices without relying on the cloud. It reduces bandwidth consumption because it can aggregate and filter data before it actually gets sent to the public cloud. Edge makes business logic available offline. You train the public cloud, you train the machine learning model in the public cloud, and then you deploy it to the local edge device for inferencing. So these are some of the use cases and benefits of using edge computing. So this quarter, April, May, and June, I am primarily focused on edge computing for the infrastructure, no, for the intelligence, and service mesh for the infrastructure. So if you liked what you have seen, do sign up for my upcoming session on AWS Greengrass. That's exactly a month from now, where I'm going to show you how you can implement edge computing and do exactly the same thing, but using Greengrass. So if you like this session, do sign up for my upcoming webinar on AWS Greengrass. And towards the end of this quarter, that is in June, I also have a session on Google IoT Edge, where I'm going to show you how to use TPU, Edge TPU for inferencing. So do sign up for all these webinars. You can register for them right away. It's available on mi2.live. I want to thank our sponsors, the Newstack, my media partner, where all the content that I show you goes to Newstack as an article, as a tutorial, as course snippets. Foghorn, one of the emerging leaders in the edge computing landscape. They're doing pretty interesting stuff based out of Sunnyvale in Silicon Valley. Portworx, a container native storage company, another Bay Area based emerging startup doing pretty innovative stuff around containers and container native storage. Thanks to them for sponsoring the MI2 webinar series. And I'm excited about announcing the next webinar, which is exactly a week from now. That's on April 25th. And I'm going to do an extensive coverage of Istio, which is getting a lot of attention. And it is not an exaggeration if I say Istio is becoming as popular and as mainstream as Kubernetes. And almost every deployment of Kubernetes now has Istio attached to it. So it is getting a lot of attention. And the next session, I'm going to do a deep dive on Istio. I might even have a guest speaker who is an expert in service mesh. So we are going to walk you through why you need a service mesh and what are the components of Istio and why you should implement Istio for your upcoming microservices project. And we'll also have live demos as usual. So if you are interested in Istio, do sign up for this. This is going to be on 25th. 9 a.m. PT and 9:30 p.m. IST. Again, you can sign up at mi2.live. So that almost brings us to the end. And like every time, I want to bring up my poll. So how relevant was the webinar content? Did it meet your expectations? So when I promised you edge computing and Azure IoT Edge, did I cover everything that you expected? I only see some of you participating in the poll. I appreciate if everyone takes time. All right. Great. Looks like everyone found this to be relevant, which is excellent. Finally, I need your honest feedback on the overall quality of the webinar. This includes everything from audio, visual, my presentation style, my delivery, the speed, the demos, everything. So again, I don't see everyone participating. I really appreciate if you can take a few seconds and respond to this poll. This would really help me tweak my content and improve in certain areas. So, all right. Thank you. Thanks for participating in the poll and giving me the confidence that the quality is maintained well. And I'm committed to deliver you highest possible technical sessions with highest quality, highly relevant and cutting edge. So that's the promise of MI2. So again, thank you for joining me for this webinar series. And I hope you found this useful. And stay tuned for the upcoming webinars. You can sign up today at mi2.live. And I will see you in a week if you're joining me for the Istio webinar or the next month when I'm doing this session on Greengrass. Thank you.